Okay. So our next talk, Andre is going to update us on srsLTE.
Thanks. So we should be running behind, and that would mean that we are in 2020 in February. It's the 2nd. It's 2 past 2.
Yes, the only day ever that Americans get their Thomas right.
And it's the only slot. Cool. So for those of you who don't know us, we're building open source end-to-end 3GPP protocol stacks. So with our software, you can build like fully in software run a entire LTE network. So you can have a UE, you have an eNode B, which is the base station, and a core network. You can run that entirely in software with userps or RF front ends. You can use the eNode B, connect commercial handsets, so your phone to the eNode B, or you can use the UE and connect to a commercial cell if you want so. And we do all sorts of crazy things with that. So we put the UEs in cars and in planes and like satellites and stuff like this. Most of us know us obviously through the open source project, and like we have a big or long history of researchers that use it for like security analysis, and that would be like a list of the GSMA, which is like a central entity that collects security vulnerabilities discovered in 3GPP stacks, and out of this list, all of those have used srsLTE, so it's pretty. So 8 out of 11 of the recent CVDs have used that. And we have a list online on srsLTE.com, and it lists currently over 165 research papers using our software for. But obviously there's other use cases, not just research or not just security research. So what I'll be talking about a little bit is the highlights of srsLTE from 2019. We're looking a little bit at 2020. Then I'll talk about a little bit about the platforms that we're targeting, because this has we've extended this a little bit, and briefly this touching continuous integration, continuous delivery, test and quality assurance in general. So in 2019 we had 3 releases. So we've been following a like a 3-month release cycle, and in early 19 we added DTD support, so time division duplexing, something that is not used here but in China. Carrier aggregation to the UE. We added a 3GPP channel simulator, so you could basically emulate a channel when it is received from the UE or transmitted at the eNode B. We added paging and user plane encryption to the eNode B and the EPC. In 06, we basically used those 2 releases, 1906 and 1909, to refactor a big portion of our protocol stack. So there hasn't been a lot of features added into this release, and also the next one. So we focused on preparing it and making it scalable for all the developments that we were planning to do. So we did it in summer, and in 1909 we started to open source the first 5G NR blocks, which were I'm going to talk about this a little bit in detail, but there were kind of extensions to protocol layers, to data plane protocol layers that we had. We started to put NB-IoT, which has previously been a closed source implementation. We started to put that open source. Through the community, we added circuit switched fallback, so that you can actually use have a network of 2G and 4G and have someone falling back to 2G for having calls.
Thanks to Howard.
Yeah, thanks to Howard for who's unfortunately sick this day. So get better soon. So we get more more additions from Howard there. We also added conformance testing. Like we started to add the conformance testing architecture there. And in 1912, so just in December, we added for the protocol layers for 5G, we added support for RRC, message packing, unpacking, and also for interacting with the 5G core, we started to add NGAP packing. As well as some side link support. I will be talking about this later on. So for 2020, we are actually planning to change our release cycle a little bit. So those past 2 years in which we've done a 3-month cycle, they've been quite stressful. Not only because it takes a lot of time to prepare releases and fix. Everyone wants to get pull requests merged in, and then you need to make sure that you do the quality assurance okay, and that everything does not break, and you don't introduce regressions. But especially the 06 and 012 release, they were quite hard because it was close to Christmas, everyone was on vacation. And then that's why we decided to go for that 6-month cycle from now on, basically, so that there won't be 2003. So we will adopting kind of the Ubuntu cycle and releasing in 04 and in 010, because that better fits our development cycle. So basically after the start of the year, you have enough time to prepare things, and at least that's what is our intention. We'll see. And then for the autumn release, after the summer, everyone comes back and you develop and test, and then you have a good autumn release. So that's what we were looking at for 2020 at least. Let's see if we change that in 21. I don't know. Okay, so what are the upcoming features for 2020? So we will add more 5G NR stuff for sure. And something that we are looking at is NSA, so non-standalone mode, which basically means that, and all deployments that are currently out there, they are non-standalone, which basically means that you always have a 4G, which kind of serves as an anchor carrier, and all the control, all the signaling is going over 4G always. And the NR is just to offload and to provide higher throughput essentially. And it only supports the data plane. So B can ask to enable a 5G bearer, and then you have additional capacity and additional channel that goes over NR. But you always need 4G, so there's no way. As opposed to standalone, where you really have on the right side like a 5G core, so a core network that exists and speaks the 5G language and can really run independently, standalone, as the name says. And as for most of our developments, we are focusing on the UE first. So this will be added in the beginning, and then later on the eNodeB. What we have done so far is the user plane protocol layers, like all the extensions to MAC, RC, PTCP, they're pretty much done. The full control plane is there for non-standalone, so announcing that my phone is able to speak 5G and stuff like this that you need to do, and that's all there. So what we're looking at now is to do the control plane. I mean, not really control plane, but the part of the NR that is still needed for, let's say, on this side. So there's still a little bit of control and signaling needed. Adding this, and then we're extending the PHY. So we will be writing a x86 implementation of the NR PHY, as well as in RFSOC, so an FPGA-based implementation that leverages some hardware FEC on Xilinx fabric. And we will targeting those. And the upper protocol layers there just run on the ARMs in this platform or on x86. So this is not this is no problem. CV2X. So basically, we've heard about car-to-car communication using 11P. So there's kind of two competing standards for car-to-car communication. One is based on Wi-Fi, and the other one is the cellular way, and that's why they put C there. So it's the cellular V2X. And so basically, what it means if you're talking in cellular context is that usually, like a phone is connected to to a base station, and there's uplink, downlink going through back and forth between a UE and a base station. And if you have two UEs that want to communicate, you always need to go through the base station. So essentially having a round trip time or a round trip between two UEs, it's like up to the base station, down to the UE, up to the base station, and down to the UE again. And the idea is, I mean, if they're close enough to each other, we could just, you know, have a side link, so SL, so let those two devices communicate directly with each other. And that's essentially what side link brings, using LTE signals, more or less, like modified versions of that, but more or less LTE Fi and 5G Fi in the future. And we have started to implement that, and we are targeting like all four modes. We have a full Fi layer implementation of SideLink, and we have joined a ETSI-sponsored interoperability testing in December in Malaga, where we essentially tested interoperability with all like implementation from all vendors, like from test equipment manufacturers, as well as all baseband chips and baseband chips that are then put into units, onboard units from various vendors, and that's something that we will open source as well in the next release. MBIT, I've been briefly mentioning that. So we've been developing this in private, but then later last year decided to open source that, and we will be adding a full file layer for the UE and the eNodeB into mainline srsLTE. And that's something that you can get then. So you in most countries, if you turn on GeoPhos4, you spot in the 800 megahertz band, more or less, in some networks, you spot something like this, which is an MBIT carrier in band in the LTE signal. Sometimes it's also out of band here to not waste those resources. And that's something that you can then sync on and decode. The reason for not putting the upper layers is only resources. So we do have them, but we need to refactor them and put them there. But the Fi will be there, and that's something that you can then have like a graphical user interface with constellation sync and some message decoding of the broadcasting messages. Then srMQ, that's something that we've been briefly talking about in the last FOSDEM, where we basically the idea is to run LTE networks without requiring RF hardware. So basically to lower the entrance level a little bit. So you can run an LTE network, but you always need at least two relatively expensive devices and a few computers. And with this you could do that basically without hardware. And for us as developers, that's pretty attractive. I mean, we do have hardware, but we want to use it for running Valgrind and then address sanitizer and GDBing stuff that you cannot do if you're running over the air with a user. So you want to run stuff faster, slower, pause, and stuff like this, and maybe emulate more complex scenarios with multiple eNodeBs that are very difficult to control and to orchestrate. And so the idea was to basically use srMQ. And instead of sending those IQ samples, I mean, we're still running the full Fi to usurp. We are, using srMQ to send it over IPC or IP to a receiver. And then we basically added timestamp synchronization for that, because LTE is very much depends on time stamps and time synchronization. So we added support for that. And then we've also removed all the dependencies from system timers in the UE and the eNodeB this year. So there's all the timings derived from the samples that come from srMQ in that case, or from the user if you run it normally. That allows you to run a full end-to-end system, like in the CMake like testing thing, without requiring containers and other dependencies. So it's very basic, but it allows you to run those things with a make test basically. And that's just a screenshot of how this looks like. So it's 3 consoles. Here you have the core network, srsEPC, then the eNodeB, and then here you have a UE that attached to, it's a great channel. Look at this constellation, and yeah, and you see like it just behaves as if you're running over the air. Very good. And it's all running on one machine, and you can debug it, you can GDB it, you can single step through it. It's all good. At least on the RAN side. Okay. SRS and eNodeB outlook. So actually SRS eNodeB is always a little bit like the stepchild of ours. So we are like focusing on the UE so much, but it's not. I mean, we really don't mean that. But the good news is that we will be focusing on SRS eNodeB a lot more in the upcoming months. So we not only add new features like handover, for instance. So this is needed if you have two cells and your UE moves. So it's leaving basically the cell range of one base station to the other one. You need to do a handover. So that will be added. There will also be support for carrier aggregation. So a single UE cannot only have a primary carrier, but you can add multiple carriers to it. So, and that's needed for for increasing bandwidth, obviously. Yeah, you can combine up to 5 in release 10 and up to 32 in theory in release 13, I think. So we'll see how much DSP we have to do that. And we will focusing on performance and stability a lot. So we're going to deploy this, and this needs to be rock solid. Target platforms. So up until now, we have really just, the priority has always been on x86. So the PHY is so computationally intense that it's not really viable to run a full LTE on anything else like the PHY, on anything else than x86. Just because all of the like SIMD that is required, and even ARM. It does have SIMD, but it's even if you have a powerful like the Snapdragon or Raspberry Pi 4, it's still hard. I mean, you can run like smaller bandwidths, like 6 PRBs is probably okay, but a 20 megahertz or 20 megahertz LTE signal, there's no way you can run the entire PHY in ARM. But it's getting better, yeah, the idea is to basically widen that a little bit, because obviously it's getting better, up until now, having focused on x86 only, we will expand that. So we do support ARM already, but we will extend this to sync ultrascale. So in fact, we have a full PHY for downlink in FPGA. That basically offloads all the heavy stuff to an FPGA to sync ultrascale plus, and only runs the protocol layers L2, L3, so the upper not so DSP critical things in ARM, and that's something that we do with the same code base. So this is not something different or a different fork or so. So we're intending to maintain this and use the same code base that runs on all those platforms. And we will see. I mean, maybe the ARM. I haven't looked at the NVIDIA ones. Perhaps they're a little bit more performant, but maybe you can even run a bigger cell there with all DSP in the ARM. That would be cool. So besides the wide range of RF hardware, we're also targeting a wide range of DSP platforms here. Quality assurance. So this is, like if you want to target like commercial grade, depending on what that means, deployments and things. I mean, you have to really look after quality, and then after regressions that you do in your development, and that you introduce, and then that basically what you're putting there to a customer, sending to a customer, or putting on GitHub that actually satisfies your needs. And one of the building steps is obviously a continuous integration platform that we have. And then we currently have around 600, not exactly 600, it's a little bit less depending on what configuration you have. Unit tests that we're constantly running in Jenkins that is building for x86 and ARM, running address sanitizer, Valgrind, limited in ARM, and then basically executing those tests on a pull request basis and periodically in Jenkins as well. So we also try to leverage from static code analysis tools that is available for open source projects, like Coverity, a tool from Synopsys, as well as LGTM. And that's something that we basically did in the last release. So by looking at the initial analysis, you kind of had a code quality batch of E, which is like the worst you can get. I mean, it wasn't that bad actually. And then we addressed a few of them. Some of them were, yeah. Anyway, so you get now a and I hope we will get an A+. So that would be the best. That's the second best. But it also depends obviously on the ratio between lines of code and errors that you have. Yes, and then obviously unit tests is not enough, so we are RF people. So we have also an RF continuous integration that we call RFCI internally, that we heavily use for finding regression bugs and things like that target or that are related to RF things like DSP and RF related issues. And we have been developing an in-house testbed where we used Jenkins that SSH into machines, launch Docker, Python scripts that post-process results and analyze logs and stuff like this, create reports. And that's also something that we execute on each pull request and periodically, like long-running handover tests, 24 hours, 48 hours that we run, weekly on a weekly basis. Something that we'd like to announce here as well is that we've recently, agreed with Cismicom that we are more closely working together and basically adopting. Because this in-house testbed, I mean, it was a good thing for us and it worked for us. But there's a tool called, a software called Osmo GSM Tester, which has a lot more features that we had, and it just made a lot of sense to kind of get srsLTE support into Osmo GSM Tester, so everyone else can use that. It's already open source. It's an Osmocom project. So we will adding Osmo GSM srsLTE support to Osmo GSM Tester, and then basically we'll rebuild that entire framework with running tests and producing logs and reports and probably also trying to make those available for the outside world. And also extend the RF infrastructure. And that's a photograph that Harald actually took. So that's an installation in Cismicom, where Cismicom has built like a rack and a 19-inch one U essentially housing that houses like various RF front ends and all connected cable together with variable antenna, all controlled remotely. So this allows you to reproduce experiments, to run those continuously, and that's something that we are looking forward to, and extending also Osmo GSM Tester for that. Another thing was conformance testing. So I will briefly touch this. So all the UEs that we have, all the phones that we have, they're running conformance tests, so they need to obey tests that 3GPP actually does. And you usually do that. You go to a testing entity, you get a Rohde & Schwarz 1 million euro thing that you can test your UE with. Nobody can afford that. So what we did is to use Eclipse Titan. It's an Eclipse project. It's a TTCM3 compiler. That is actually the language that the conformance tests are implemented in. and basically wrote a system simulator that basically acts like this guy without PHY, fake PHY, and that's something that we can run on the Raspberry Pi. It's all integrated in our continuous integration, and this is something that like really helps to make sure that the UE actually does what it is supposed to do, and it complies with all the all the conformance requirements on the protocol side of things, and we are running fully unmodified protocol stack there to test against the tests, and that's it. Thank you.
Is your ZeroMQ transport LTE specific in any way, or
No.
usable by any sort of RF?
No, I mean there's like we have.
Please repeat the question.
Yeah, sorry. So is our srsMQ transport LTE specific or not? There is like timestamp synchronization and resampling, and the resampling thing is something that you just put a base rate, because how the UE connects to a base station depends on the bandwidth. So it first surges in a lower bandwidth, then changes the bandwidth. So you need to do a little bit of resampling there. But I mean, other than that, no, it's not LTE specific at all. No. Yeah.
You look at implementing that on the Pluto, or
Thanks for that question. Yes, the question was if we have been looking at the Pluto to implement LTE. Yes, so two things. The Pluto, like LTE, is like really requires strict timing. So we need to know when we receive samples, what the timestamp is, and when we transmit them, because the transmit is always aligned to the receive side. And what we need to add there is timestamp support, because the Pluto libIO doesn't have timestamp support.
That's something we're adding this year.
Very good. We're really looking forward to that. So then the extension of that would be, yes, you could perhaps run the MBIOT on the Pluto itself, definitely on the host, but you still have your USB 2 bandwidth limitation. So you can definitely run the MBIOT, and probably is like a small LTE cell, 6 PRBs, 15 PRBs, but definitely not the bigger ones, because they're like 20 megahertz. So you're not getting that over the USB 2.
one remark. If
Yes.
you're going to Jenkins, there are better alternatives.
Oh, okay. Thank you.
What's your plan on getting a better tool chain? And
Yeah, I mean, we just use Jenkins for continuous integration, really. So it's not.
are you already using it?
Oh yeah, it's deployed. Yeah. Yeah.
We have the next presenters.
Of the CRMQ?
Cell broadcast, like sending SMS when there are an alert or.
No, I mean we don't. So the question is if we have SMS support. So no, we don't do that. I mean it's possible to send SMS over NAS signaling from the EPC, and I know of like a few like users on the list who have looked into this, but it's not officially supported in the open source list. Okay, yeah, it's. Yeah.
Is it possible to change the frequency, the channel plan, for use it in 70 centimeter length?
Yeah, I mean, yeah, ham radio, yeah. So I mean, there's a few ham radio users I know of, and then obviously, I mean, the limitation is the RF that you're using, and we are agnostic. We are RF agnostic, so we can.
Already in the source code, and I think about I was not sure if I should change existing channels, the GSM channels, to my frequencies, or add additional channels.
Yeah, I mean, like, so there's a like, we have a lookup table for all the 3GPP like official channels, and maybe you cannot directly use your channel of interest because it's not an official one, but you can obviously add this if you want. Yeah, I mean, I don't see a problem there. Yeah.
I think it's easier when